seminar. And as most of you probably know, every month the Advanced Grid Institute hosts a seminar during your weekly ESIC seminar series. The Advanced Grid Institute is a joint institute between Washington State University and the Pacific Northwest National Laboratory. I'm Jeff Daigle, and I serve as a co-director along with Dr. Noel Scholes as directors of the Advanced Grid Institute. Today, I'm pleased to invite two researchers from the Pacific Northwest National Laboratory to share a presentation on pathways to net zero in the Western U.S., considering the impacts of climate change, resilience to climate extremes, and equity. So this is a very timely and important topic that a lot of people are paying close attention to, not only in the energy industry, but also government agencies at the state and local level, as well as federal level. So our presenters today are, first is Dr. Natalie Voisin, and she is a chief scientist for regional water energy dynamics in the Earth System Predictability Group at the Pacific Northwest National Laboratory. And she works on hydrometeorological forecasting and coupling of human Earth system models to understand critical energy water systems. She's well researched and has published many papers and leads several projects at PNNL for a variety of clients, mostly U.S. Department of Energy offices. She joined PNNL in 2010 after completing her doctorate degree in civil and environmental engineering from University of Washington, and also has a master's degree from McGill University and bachelor and master's in engineering and hydraulics and fluid mechanics from the ENSEE-IHT Engineering School in Toulouse, France. Joining Natalie is Dr. Stephanie Waldhoff. And Dr. Waldhoff is a senior research economist, team leader, and interim director of the Pacific Northwest National Laboratory's Joint Global Climate Research Institute in College Park, Maryland. And this research focuses on the long-term effects of climate change as they relate to the economy. And prior to being at PNNL, Dr. Waldhoff has served as an economist for U.S. Environmental Protection Agency's Climate Change Division, looking at integrated assessment modeling and estimation of economic damage from climate change. And she received a bachelor's and PhD degrees from the University of Chicago. So Natalie and Stephanie, please take it away.
Thank you, and thanks for the opportunity to present. I think Jeffrey said it's very timely. It's all the more timely that today is the release of the National Climate Impact Assessment. And so this research is very, very relevant.
Amazing.
All right.
Hey, Janine, can you guys mute the room, because we're picking up some background here. I think it'd be easier for the folks online if the room is muted until you guys have questions. Thank you.
Sure, we'll ask everybody, please make sure you mute inside of the conference room.
Okay. And I can't see you anymore as I'm presenting. So please just interrupt me if there is anything going wrong or questions or anyway. So first, let's start for some of the motivation. Those are some of the administration goals. I have 100% carbon pollution-free electricity by 2035, net zero emission no later than 2050, and 40% of federal investment to disadvantaged communities. Those are the goals of the administrations to combat climate change. You may wonder, how did we come up with those numbers? We use a number of multi-sectoral model. This is what you can see on the right here. Those are projections across different sectors to understand what are the decrease in energy emissions by sectors needed to reach net zero. So what you can see from 25 to 2020, in blue, you have the electricity sector, and the electricity sector has already started in transition. In red, this is transportation, green is industry, and yellow is the buildings. And then you have the net zero in black. What you can see is that if we want to reach net zero, drastic changes are required. And this is the case for any type of policies that are needed. So that's the range that you can see, is uncertainties associated with different net zero policies. For all of them, it's a drastic change. And you always go first with the big emitter. And so the greatest reductions need to come from decarbonization of electricity generation, followed by the electrification of transportations. There are significant uncertainties in how to move forward given the cost of the transition. It's one thing to make it happen, but will we be happy about it? Can we sustain it? Can we even do it from a social perspective? So this is really this other piece on how to get to that J40 and introducing that equity and environmental justice concept. If you look at that at those picture at the bottom of the slide here, we typically see those transitions from a provider's perspective. We're trying to look at how we can get that net zero transition from an infrastructure design, reliability requirements, investment and stranded assets and cost of operations. We're seeing it from the eyes of good engineers and scientists, engineers. But if we want to ensure a successful transition, it needs to be adopted. And it's going to be adopted if we can demonstrate that those pathways to net zero are affordable. We understand the impact on jobs and income. We understand the impact on underrepresented communities and on the environment. So those are our consumers. You need both providers and consumers, and it's very hard to bring those two together. So this is why we now have federal and state regulations to ensure the consideration of environmental and energy justice. It ensures that both of them are considered in those roadmaps to net zero. We have energy equity related measures in 22 states. We have caps limits in rate increase associated with generation mix. And we also have utilities required to address equity and environmental justice in their long-term planning. And here it's done a little bit differently. It's done through regulators. The point of this slide is to show that first, you need to really have the two perspective. When you evaluate roadmaps to net zero, you have to look at it from a provider and a consumer perspective. And the actionable insight will be to both utilities, investors, but also regulators. That's something that is new in how we want to proceed with getting to net zero. So let's get back to our traditional way to do long-term planning. There's typically a three-step process to do that long-term planning in the electricity sector. First, you start with a scenario analysis. As part of this process, you evaluate the combination of climate scenarios, technology, taxes and incentives, market structure. This is the prior graphic that I was showing. We're looking at the big picture and what may be the impact on the different industry and the sequencing of the electrification of the different sectors. At that stage, the people that are being engaged include regulators, generation-specific interest groups, power reliability committees. The next step, that typically those steps are pretty well coordinated, is on understanding how to make it happen. So we use a number of models to understand what the infrastructure would look like. We are looking at 10, 20, and 30-year build-out. This is when we're also looking and developing a lot of the wind, solar, load, and hydropower data sets that are going to inform the power system models. We're doing a lot of assumptions on the fuel prices. At this step, the targeted users includes the power reliability committees, utilities, RTO, ISOs, investors, and also all of the production cost model software companies who are then going to support a lot of the third step. Those two scenario analysis and infrastructure planning, the outcome is really a portfolio of sited infrastructure and understanding how much it costs. Those are what we call the preferred portfolio. The third step is the number of users, as more you go to the right, is just increase exponentially, and the diversity in studies also increase exponentially. It's the operation planning investment. This is where all of the, from the community, from the power systems, everybody has their own unique question on understanding electricity prices, on understanding what will be the operations of hydropower in the past. Will there be a curtailment for wind and solar? How much transmission should we consider? How to size and manage storage? What will be the performance of the grid under extreme events? Yada yada. So that's all of those steps. What we've noticed, and that's an observation and really technical gaps, is that all of the different users are outsourcing this information, and they've been done in silo. So the first thing that if we want to bring climate and social science, which are needed to move forward to reach the net zero, we really need to bridge those silos, making sure that we have consistent information, especially on climate and social science across all of those stakeholders. Um, so that's one of the things that we've been working on, and the way, what does it look like? What could it look like? What should it look like? Um, from the scenario analysis, what stakeholders can expect is those decarbonization roadmaps. What you have on the left here is those are the roadmaps. So this is a generation mix for 2050 under a net zero policy for the Western US. The different colors are for the different technology, and this is the type of format that the stakeholders at that stage understand and can evaluate what will be the different technology at the big pictures needed to get there. There's a lot of more data sets at that stage, but that's the one on the electricity sector. As you move to the right, we need to downscale that information and evaluate what the infrastructure would look like. So this is what you have. An example is the sited infrastructure. Each grid point is added wind plants. And that's something that would be very new here, is making sure that it's not just at the scale of the power system model, it's actually geolocated within a 1 kilometer. And that is what brings the communication beyond the power systems and the energy sectors. It opens the dialogues with the community, and Stephanie is going to talk more about this. That provide the insight on energy and economic security on communities, and that's information that can be provided to regulators and states to understand really a bit more where this would be, who would be impacting on jobs and incomes. That's really where that fits from. And then more going to the right, more than in everyday operations, is using a catalog of extreme events and development of climate intelligence to size and manage storage, develop market incentives, and evaluate new transmission. It is important because as the generation mix is evolving, we're going to have a different dependency on climate. So we can't operate the grid of tomorrow, as of 2050 and 2035, the same way that we're operating it today. There's way more information about climate that needs to be integrated so that we have the best use of resources with resilience and affordability. So you can imagine a lot of people are going at the table to go through this information. So it's important that this information is consistent across the different steps to bring robustness, confidence, and most important, trust, so that we can have actionable insights on building that net zero economy. So that looks aspirational. This is great. Well, we actually did it. So those are all the models and the data sets that we've put in the background together to address and represent and provide those results to stakeholders. We have on the left side, we have climate and multi-sectoral models that provides those roadmaps, and a catalog of future roadmaps. Those roadmaps are then translated into that second step with a bunch of models: electricity, transportation, renewable generation, plant siting models, with a consistent climate and consistent policy and assumptions. All of those data sets and models are then also going all the way to the right to understand everyday operations, reliability, emissions, and unserved energy. And to go even further, we then have social equity impact models that allows to evaluate those roadmaps from an environmental and equity perspective. There's a lot of innovation that went into that process. It has to do with the models that we customize, but most important, it's about all of the connections. I also want to mention that this is not an Uber model, like there is going to be only one way to do it. I think we mentioned we want to bring people at the table. It means that any stakeholders at any step can come in this workflow and substitute their models or get intermediate data sets and do their independent analysis. And that's with this transparency that we bring people at the same table to understand what if, but have you considered this and that? So this is really a new ways to communicate and achieve success. Where to get it? We have a web-based platform with open source resource and detailed documentation. It's at goodip.pnnl.gov. There are multiple tabs, some where we talk more about the science and some where we talk more about the resources with more information about all of the models that we developed or the one we used if you have interest on using your own model as part of this workflow, and also get access directly to all of the data sets if you want to do more analysis on the data sets. We only really scratch the surface. So those are the just the snapshots on the vetted data sets so that you can find them out there. We also have some visualization that can help understand what's happening. More is needed, but it's important to put it out there. And we really want, it's really an opportunity to present to you all today so that you can look at it. Something else to mention is that those are reproducible open source workflow. This is the state of the art where each of our tools and connections are thoroughly documented as part of GitHubs and Zenodo for the data sets, a thorough documentation that allow any of you to go and pick up the models and run it yourself if it makes sense for you. Even though this is open source and you could run it, I always encourage collaboration, because even though if this is thoroughly documented, there's always questions on making sure you use the right model for the right questions. And so we've thought about it, and we would love to accelerate the science with you. So just a call for, here are all of the models, go have fun. We would love to have fun with you too. And since we've thought about it, we could really help you also in getting faster. So that was kind of the little speech of where we are, but I want to present perhaps a little bit about the meat of what we found with this experiment. At this point with the workflow, we've been looking into how to evaluate stranded assets. Stranded assets is when you build some of the, new plants, but they will not reach the end of their life due to early retirements, or there will be environmental and societal challenges to siting of power plants, and they will, you will not get the permitting, or you will not just get back into your return on investment in general. So those are the questions that we had and that we are addressing. We're also looking at questions around the electrification of transport. With our research, we're looking at how, with the electrification of transport, there's going to be a change in the peak load, and specifically the sensitivity to air temperature. A lot of the load forecasting is based on econometric model, but that's based on the past sensitivity to temperature. So we are updating this sensitivity to air temperature to better understand the stress on the grid and potential vulnerability. We're also looking at extreme event case studies. We mentioned that a lot of our stakeholders or reliability councils and utilities. And at this time, they're really interested in understanding how their plants are going and they're going to behave under worsening of extreme events and heat waves in particular. So we do have heat waves characterization and standardization of severity, frequency, and impact that I will also go through. Energy droughts is a new concept. I mentioned that you should not operate the power grid as of today the same way that you should operate the grid of tomorrow because of the changes in the generation portfolio. That climate intelligence is huge. And even though we are looking at heat waves and droughts, there are also what we call Dunkelflaut. Energy droughts is a more common term. It also allows to evaluate not just wind and solar, but coincident wind, solar, and hydro with peak load events. And we are working on this concept to evaluate the energy storage siting and sizing. Okay, that's a lot of talking, but I will make more sense in just a minute. And then we're looking at the affordability, jobs, and incomes, and then the disadvantaged community that Stephanie will go through. So let's talk a little bit more about the results, those roadmaps. Um, I started the presentations with that 2035 decarbonized grid and then net zero economy by 2050. So what we currently have with the current policy here, you're looking at the generation portfolio in a 5-year increment like before, and each color is a specific technology. So that light blue is actually hydro, that dark blue is gas. When we talk with the industry, when we develop them, they ask that there would be no gas with carbon capture sequestration. So that's why you do not see it on this graph, but we do have some simulation with it. What I'm trying to demonstrate on this one here is that to reach the 2035 goal, even the current policy is not bringing us there. You see on the left and what is needed to reach our net zero goal on the right, we need to go faster. We need to have a retirement of gas and we need to have and double the capacity in solar and same thing for wind. That's actually also one of the takeaway from the National Climate Impact Assessment on the energy chapter. We need to go faster if we want to go and reach our net zero goal. That's by 2035. The other goal is by 2050 to have an electrification of a deep electrification, transport, but also all of the other industry. At this time, with the current policy, we're not getting there either. So this type of information is really for policymaker to make sure that we have that signals. We're doing great. We're doing better than 20 years ago, but we need to do more. So that's at a high level picture, but now we need to say, okay, but how does it look like right now? So that's the siting of the infrastructure that I was mentioning. This is a bit more detail of where, here this is an example of what a sited infrastructure for the state of Washington is being done for the entire US. But just here so that we can appreciate, we have that sited infrastructure by 2035 under a net zero scenario. So this is what would need to happen to meet the goals. They are located. It's not a simple, it's actually a complex siting process. There are a number of knobs depending on the climate. Here we use an RCP 8.5 SSP5. Might be gibberish here. It means that this is one of those extreme hot, warmer climates. So we can have a knob on the climate, on the type of net zero policy with more depending. There's a lot of knobs on even if it's net zero, depending on how you do the land uses or different technologies like CCS that we mentioned. There is the time horizons, but also some of the priorities on land use decisions and community decision. So this is really the type of graph that we're showing to start engaging with the stakeholders and make sure that we have the adoption of the technology. I talked about climate, how the climate is consistent throughout the process. This is here just to illustrate the future climate data sets that we are using. As you might know, there's a lot of climate data sets out there. The one that we selected is for one of those hot scenarios. And where it's specific is its ability to demonstrate extreme events that you had in the past and what they would look like in the future. That's what you have here on the right. You have one of the heat waves in July 2018, and what these same heat waves would look like in the long term. This is the type of scenarios, this is all a communication exercise. At this time, a lot of the climate data sets are out there. They're going continuously to 2100, and you have 6 or 7 different ones. When we talk to the electricity sectors and we're looking at 2050, they want to use, and there is some misconceptions that the projection for 2050 is what will happen in 2050. This is just a representative year. And so because of those communication, as we are learning more and more together, this type here of this data sets is more intuitive. We get a lot of questions of what about the heat dome in 2021, about the cold snap that we had in 2022, and that's something that is easier. This being said, we could use other data sets moving forward, but that's what we have right now, and stakeholders appreciate the way that we can communicate what the future climate is. Now that we have the future climate, we also have future load. We're using loads that are responsive to extreme weather and electrification. As you can see on this graph here, the load, we are doing it at the scale of balancing authorities, and we have it at the scale of balancing authorities and counties. That's allowing us to understand the shift in populations, but also to translate it to the scale of the power system model, and really also to demonstrate that when you have a heat wave, it's not 30% warmer everywhere. There's a lot of spatial and temporal variability on how the heat waves go left and go north and south and east and west. I talked about some of the questions that we are addressing about temperature and electrification of transport. It's important to know that 10 to 20% of the system's peak load is impacted by transportation load for the overall Western interconnect. And there is a lot of uncertainties on the electrification rates for transportation and also on the charging strategy. So the two graphs that you see here on the upper left is to really understand the sensitivity of that peak load first just to temperature. And we can see that if the benchmark is 20 degrees C, which is pretty, it's like 60, it's like 72 for summer, that would be about pretty standard. If it goes to 40 degrees Celsius, which is over 100 degrees Fahrenheit, you have a plus, an increase of 40% in your charging power. So that's a 40% uncertainty associated with temperature. If you look at that benchmark, that's purple that go to the right, and then you see the changes in charging strategy. You can see that, especially during peak hour at about 5 o'clock in the afternoon, depending, you can go from plus 15 to minus 30%. So your uncertainty associated with the charging strategy is a bit larger than your sensitivity to temperature. Interestingly, it means that when you have heat waves and cold snap, it means that it will multiply the transportation peak loads demand. What we're seeing from this graph too is that with charging strategy, you can also alleviate that sensitivity to temperature by pushing it across the different hours. So that's an opportunity where there's a lot that is being done and needs to be done. When we work with the reliability councils and utilities, a lot of the questions we have typically are, how do we put cold snaps or heat waves in our power system model? And we could provide our data sets, and we're providing our data sets of load, wind, solar, and hydro. But that's just one thing. We also want to understand with the stakeholders how to set it up properly. And so we analyzed the hottest and coldest day of each year over over a 40-year period in each balancing authority in the Western US. And that's what you can see on the right. At the top is for heat waves. At the bottom is for cold snaps. And so we centered at the hottest day and the coldest day. And then we're demonstrating that typically heat waves and cold snaps last about 6 to 7 days and are on average symmetric about the maximum and minimum temperature day. And this catalog of extreme event is very useful to talk with the stakeholders that you do not need to run for an entire year for heat waves and cold snap. You can put and you can engineer heat waves and cold snap directly in some of your data sets. And then we're providing a lot of insights on either you use directly the data sets we have or by how much to rescale your load in by numbers that are realistic. I mentioned that we have wind, solar, and load and water that are coincidence. That coincidence is key. And so we've been uniformizing the concept of energy droughts. And what you have on the left are each dots is showing how many energy droughts, so compound wind and solar together, when you have the lowest wind and the lowest solar together for the worst 1 hour of that year. And it's a 1 hour that's good for it's the timeline, the step is very important for storage. So what you can expect from this graph here on the left is that California has about 10 compound droughts a year on average that last up to 18 hours. You can see that over ERCOT and the Midwest, those droughts are going to be a bit longer. And that's important because right now the storage is being managed in a timely, from day to day. So you can see that California with their own storage, if they size it right, they're pretty independent. When it comes to the Midwest, they're going to likely need to manage a bit differently or rely on transmission because those worst droughts are really happening and they last more than a day. On the right side, we chose a time step of 1 day. It's important because you kind of have the lowest wind and solar compounded. And if it goes over an entire day, then it's going to affect your recharging of storage. And what you can see now with this, the same representation, is that California has up to 4 compound drought a year as of today. On average, that lasts up to 6 days. And what we're seeing is that those frequency of droughts decrease with longer timescale. California has the shortest hourly compound droughts, but the longest daily droughts. What that means it has implication for how to manage the storage. This is today, so this is going to be worse moving forward. It has impact on how we manage storage. It can't be day to day anymore because else you won't be able to recharge it, and how you rely also on transmission. I talked about long-term storage, so I just want to provide ideas here, and this is work done also by the team on seasonal energy droughts. It's important here, those are the load, the wind and solar for all of the different balancing authority over the Western US. What's important to see is that each balancing authority is very different. Sometimes you have complementarity between wind and solar. For example, over the name Pacificor East, you can see that during the highest peak, the highest in summer, you have the lowest wind and the lowest solar, but over Montana, it's going to happen in winter where you have a winter peak, but you also have wind and low solar. So it's important to start playing with that complementarity, understanding in which regions you have complementarity. Those regions can be pretty self-sufficient. In places where you don't have that complementarity, you want to understand what's happening into the other balancing authority for transmission. As we go to seasonal drought, it's going to be important to include hydro, natural gas, and transmission for all of that storage capabilities if we want to be efficient. I think that for time, I'm just going to pass it to you directly, Stephanie.
Okay, thanks, Natalie. So first, I want to present on the motivation for the research we're doing on energy and economic security, and then give a brief roadmap for what I'm going to share. The impacts of the net zero energy transition that Natalie just shared will also have profound impacts for the people who use the energy and for those whose jobs are in the energy sector. So we're going to be focusing on questions around energy and economic security, such as how will consumers' energy security be impacted by a transition to a net zero economy? What types of jobs are going to be created or lost, and where will those jobs be located? And what are the implications of those job changes for consumers' incomes? And in particular, how are disadvantaged communities going to be impacted? Next slide. We've developed multiple metrics of energy and economic security at a range of spatial and socioeconomic scales. We also did some additional model development, but I'm not going to focus on those today and just look at how we quantified the impacts. So we measure residential energy security for 10 income deciles at the state level. We're looking at changes in jobs and incomes at resolution that vary from the county to the census block level. Currently, we're just looking at Washington State. And we're also exploring disadvantaged community status, or how these changes could move a community into or out of disadvantaged community status, and that's at the census tract level. Next slide. Like I said, I'm not going to go into the details on the modeling, but we have a webinar you can look at to learn more about it. So first, I want to talk about our measures of energy security metrics for each of the 10 income deciles in every state. We use GCAM USA for this analysis with the same scenarios that Natalie just presented, the business as usual and the net zero energy transition. Energy security can't really be measured with one single metric, so we project 3 different metrics for each of these scenarios. First, the consumption of energy services, which is how much heating, cooling, and non-thermal residential energy services that each of these 10 income deciles consumes. So the reason we're looking at service and not energy consumption is that less efficient technologies require more energy to get the same level of service. And what people are really concerned with is how much heating they get. And it's not about did we use this amount of energy, but how much heat we got for that energy. We also look at the satiation gap, which is how far the consumer groups are from their ideal level of energy service. So are they able to fully heat or cool their homes and have the desired level of lighting and refrigeration? And we measure this for each type of energy service. And finally, we project the energy burden, which is the percent of household income spent on residential energy services. Next slide. So looking first at the gap in residential heating services for 3 deciles, we're looking at the lowest income decile, D1, a middle income decile, which is the 5th one, and the top income decile, D10. So looking at current conditions, so 2020, and then a projection of the business as usual in 2050 on the bottom row. And here, a larger gap means there's a bigger difference between consumers' desired heating level and what they actually have. So bigger is worse. And we see that across the board, the lowest income group has the largest gap between the actual and desired level of heating. Over time, as incomes in all deciles are growing through 2050, those income growth will improve consumers' ability to afford their desired level of heating service. So by 2050, the lowest income deciles in most states have moved into the moderate comfort category, and the middle income deciles for most states are in the high comfort category. And I want to note that this is just for heating services. If we were to look at cooling services, the distribution across states and income groups could look quite different, especially over time as the need for cooling will increase with climate change. Next slide. Now turning to the effect of the net zero scenario. So here, the top row is actually showing the exact same information as the bottom row on the prior slide. It's the business as usual in 2050, but it's now got a continuous rather than discrete scale. The bottom row here shows the difference between the net zero energy transition and the business as usual in 2050. And because a larger gap is worse, an increase in the gap means a decrease in consumers' comfort levels. So we saw that the net zero scenario causes huge increases in electrification, which is generally more efficient than the technologies it's replacing. So it requires less energy to achieve the same level of comfort, but we're also facing higher electricity prices. So the net result is negative, resulting in lower consumption of heating services, particularly for the lowest income group. And in some cases, we see an increase of up to 10 percentage points, with the larger impacts generally in the colder climates. Next slide. So now turning to residential energy burden. Again, this is the share of household income that's spent on energy. And the pattern here is actually quite different, with more states having high shares of income spent on energy in the middle income decile, both in 2020 and in 2050. This difference in pattern is because at the lowest income deciles, the consumers are likely making choices of food or fuel. So as we saw, they're quite far in some cases from their desired comfort levels. So they're not spending a huge fraction of their income on energy, but they're also not using very much energy in a bad way. So as incomes increase in the mid-range, those higher income levels allow consumers to get much closer to their desired comfort levels, and they have enough income to not have to choose between necessities such as eating or heating, but they're spending a significant share of their income to get this level of heating service. Next slide. Again, here the top row is the same information as on the bottom row of the previous slide. And looking at the effect of the net zero scenario, we can see that the increases in energy burden are largest for the middle income group, but even in the low income groups still have increases close to 1 percentage point for many states. And considering this group is very likely making choices between food and energy and other necessities, it's a fairly significant change. Next slide. So there's a lot of results on the residential energy security that we don't have time to look at today, but some of the key takeaways from this research is that in addition to income, the influence of decarbonization policies play a significant role on residential energy security. Decarbonization policies have different impacts on residential energy security depending on which income group you're in, with the most significant impacts observed in the mid to low income groups in terms of energy burden and the satiation gap, which we looked at. Some metrics don't look as severe for the lowest income groups, but when we look at them together, we can understand why the picture is actually worse for the lowest income groups. So it is clear that a comprehensive set of residential energy security metrics is really necessary to see the full picture of what residential energy security will look like. Next slide. So now turning to the economic outcomes that we looked at, this work is ongoing. So I'm going to present the goals of the work and some illustrative results. The overarching goal here is to look at the economic implications in terms of jobs and incomes, particularly for the most vulnerable groups, which we define as using the White House CJUST method for disadvantaged community definition. Next slide. So first, we're looking at how changes in the electricity generation sector will impact jobs and income at finer spatial scales. So here we're looking at counties within Washington state. The work is done using the in-plan model, which is taking outputs from GCAM and SURF, which Natalie presented results from, to identify changes in industrial sector composition and new electric generation investments, particularly where new plants will be located and older plants may be retired. Next slide. This work, we can estimate doing this work, we've estimated impacts down to the census block group scale, but those are really difficult to look at on maps. So here, the maps we're looking at just are showing some illustrative results at the county level. The employment in each county for both direct jobs from new and retired plants, which include construction, which are temporary jobs, and operations, which are long-term jobs. Next slide. And we can also look at indirect jobs, which kind of come from this trickle-down effect of increased employment in electricity generation. So we can look by individual sector and also at totals across different counties. Next slide. These changes in jobs, both by sector and type, can be converted into income changes. Again, we're showing these at the county scale, but they can also be downscaled to the census tract or block group level. Next slide. The finer resolution is necessary because it enables us to project whether currently disadvantaged communities may be more or less likely to continue to be categorized as disadvantaged communities with these changes in jobs and income due to electricity capacity expansion. Next slide. So Go Deep was a $4.3 million LDRD investment from PNNL. We had scientists coming from many disciplinary backgrounds, hydrologists, atmospheric scientists, economists, electrical and software engineers, and experts in stakeholder engagement. The work has really demonstrated the importance of a fully integrated modeling approach to energy transitions in order to provide insights to policymakers that are at decision relevant levels. The next steps for this work include exploring additional outcomes, models, and drivers, including distribution, the next generation of power system models, local energy efficiency adoption, and market incentives. Developing climate data sets that can help support questions that are more focused on infrastructure and community concerns, and exploring how we can integrate energy and economic security and equity concerns and outcomes with bottom-up energy efficiency adoption measures and regulatory decision making. I think that's the end of the slide. So thank you. And I think Natalie and I can take any questions.
Great. Janine, do you want to help with questions in the room there?
Yeah, I have a question. Very nice presentation. I just want to know that for the generation expansion planning, you told them by 2050, the most share will come from solar and wind, which is highly uncertain. So do you see that what kind of measures like on the storage or the load management side you need to take to achieve that net zero by 2050?
I can take this one. So you're absolutely right. We see a lot of wind and solar, which the work that we're trying to demonstrate is there is the work on the intermittency. The intermittency, it's at a very fine scale, and the questions will be on how much reserve you need. And so we didn't go to the reserve, we focused here on the generation, so that it's this is part of more work that needs to be done with the future grid. What we have, so not within at sub-hourly with that stochasticity, is really looking at then half an hour, 1 hour, daily, where this is not an intermittency that is random, it's associated with climate patterns that we can predict. And so a lot of the work that we do has been really at those other timescales that allow us to really provide what we call this climate intelligence, because typically when it's windy somewhere, it's not as windy somewhere else. So understanding that spatial and temporal coincidence so that we can manage storage or we can manage other resources like hydropower that can shift some of the generation based on those needs. So that's where that wind and solar, those are all of the opportunities for research with wind and solar. It doesn't mean it's less reliable, it just means we need to work smarter.
Yeah, thank you.
I also have a question. Did you guys look into the coupling between a net zero grid and extreme weather events and compare that to business as usual? And if so, what were some of the major changes found of how the grid reacts to some of the climate events in the future?
So we did it. Actually, Jeff, I'm going to deflect to you because that's part of the National Transmission Planning Studies. So a lot of this work has been also used in other projects. And I think that on the NTPS, Jeff, you did exactly that with transmission.
Yes, we did. So just to clarify how these projects fit together, the Go Deep initiative that Natalie and Stephanie talked about, that's what we call laboratory directed research and development, or LDRD, and that's internal investment on building and developing new capabilities that might be relevant to our projects that we do for the Department of Energy or other clients here at the National Lab. And we're different than the university. Our funding comes from these projects. You know, we don't have people here to pay tuition to be part of the organization. So that's we're a client-funded R&D organization. So on one of those client-funded projects that Natalie mentioned is the National Transmission Planning Study. This is sponsored by the U.S. Department of Energy. We're looking at the transmission scenarios for the year 2035 that support 90% decarbonization by then. The reason why we're focused on 90% versus 100% is as you might imagine, when you do these models that include production cost models and power flow analysis and things like that, assumptions you make about the dispatchability of resources is that assumption is a huge sensitivity on the type of way that the grid is dispatched. So whether storage is cost effective, or if we have hydrogen, or if we have small modular reactors or other types of technologies to provide that dispatchability that you can't get from the wind and solar, those changes make a huge difference. But if you allow 90% decarbonization instead of 100%, then you can have a little bit of natural gas to provide, peaking services for peak load and things like that. So at any rate, we did look at extreme events, or resilience to extreme events. We conducted both production cost models. So a production cost model is 8,760 hours for a reference year. And again, we're projecting things forward to 2035. And then we extract the snapshots from the production cost model to look at power flow analysis. And our metric that we used for the extreme loads is unserved energy. So this would be equivalent to, like you've heard the term, rolling blackouts and things like that. So when the grid is overwhelmed beyond its all of its generation resources, there's a term called unserved energy. And so what we try to do is minimize that based on these transmission options. The method that we used to project that 2035, so we focused on extreme heat for that. We didn't look at cold snap. We looked at a heat wave. And our methodology that we used is we looked at two reference prior heat waves that we had, one in the Pacific Northwest and one in California. And then we projected those forward to 2035 based on it's a RCP 8.5 climate assumption. So that's how much global warming we would, or changes in temperature that we would expect for those conditions. So we disaggregated the temperature dependent load, projected that forward to 2035 with those climate change assumptions for 2035, came up with hourly load profiles, and then looked at the different scenarios for unserved energy. And in addition to that, we also stressed it based on a hydro drought scenario. And so for that, we used the 2001 reference. So that was if you remember anything from your history of the grid or anything like that, 2001 was a very extreme drought that we had here in the Pacific Northwest that affected the hydro generation. So extreme that it was creating rolling blackouts in California in the spring because they weren't getting the hydro that they would normally expect during that time. So we added that into the scenario as well to compare the unserved energy under these different scenarios. Our objective in this study was looking at the impact that transmission would have to reduce the impact of that. Because when you have a high temperature in one part of and our focus was the Western interconnected grid, by the way. So within the Western grid, if you have extreme temperatures in one part of the grid, the ability of transmission to bring in resources from other areas to help mitigate that and reduce the unserved energy is part of that analysis. So it's probably a way longer answer than you intended when you asked the question. It's an excellent question, and it's the type of thing that we do indeed pay attention to. And the data from the Go Deep team was very helpful in the climate aspects of that modeling.
Okay, thank you.
I think I have a backup question for that. So from the data that was showed, and it looks like the solar and the wind is actually like in 2050 or so, the solar and the wind will be providing more than 90% of the energy mix. And you mentioned something about still having some conventional generators that can ensure dispatchability of the energy, right? But are we also is the Go Deep project also paying attention to the system inertia, right? Obviously, because when we have so much IBR rich system in the energy mix, obviously we would be having a very low inertia, and in a case where we have a fault in the system, is there concerns about how this would affect the system inertia and how the system would respond to something like this?
This is another very good question. Go Deep doesn't do everything. It's really, I think, a combination of projects, and you're absolutely right. Inertia, in particular, is coming up in a lot of the discussions. I believe that it was part of Jeff, the NTP as well. That's why they use power flow models in the NTPS. And I would say that my heart is going on the hydropower technology. And as part of, we also use a lot of this research to understand what are the opportunities for other technologies. Inertia is not one of the monetized services. And so as we move forward with the new generation, that type of generation mix, we need to understand what are the market incentives to make sure that those type of non-monetized services are going to be monetized in the future. That has to do with the way we operate the grid today and the way we market it. It doesn't mean that this is going to be what we do in the future just because of inertia, not monetized, and there are a number of other services that we need to review to make sure that we operate the grid in a reliable way moving forward. And the only way it can be reliable is if you have the market in the background ensuring that storage is managed in a way that it will support, like, don't do every day, keep it a little bit. It might look like a loss, but during those events, they're going to be the ones saving from the blackouts. And so same thing for inertia. I don't know, Jeff, if you want to complement.
Yeah, no, great answer. And just to build on the storage piece, we think that storage is going to play a crucial role in not only the dispatchability of wind and solar, but also some of these other grid services, like voltage support and inertia and things like that. There's also a great deal of interest and effort on the topic of grid forming inverters. And so some of these wind and solar resources may be able to provide some of these fast acting response, to provide some of the necessary system services. And maybe some, you know, an alternative to that could be a fast-acting demand response to provide primary frequency response. So there's a lot of research questions about, you know, what do we do in an IBR rich or extensive IBR deployment in future power grids with things like inertia and voltage support and things like that. But I do think that there's a great deal of effort on that to solve those problems. So this slide here and this focus of this analysis is just on the energy budget for the, you know, for the total system. There's a lot of details that would go behind that in terms of the dispatchability and the not only hour to hour but moment to moment type of response that you would have to off normal conditions. So I think we've reached the end of our time. So let's all thank Natalie and Stephanie for a great presentation. And thank you all for your participation in today's Advanced Grid Institute seminar series as part of the ESIC weekly seminar series. So have a good rest of your day. And let me just conclude by saying go Cougs.
Thank you.